Bon dia a tothom. Welcome everybody. So this is the a session, especially in the Master of the Physics of Complex Systems. This is the first day of the master, and your students have had the first session some minutes ago with some introduction to the master. And this second session is to recognize what has been selected as the best teacher in the past year based on the opinions of the students and also on some objective and data on the implication on the master and this kind of things. So this is the second activity of the master today, and the third activity will be the beginning of the classes at 11 in the Alcover building, just in that direction. Okay, so just I am Emilio Hernandez, the director of IFIS, the institute managing the master in the physics of complex systems. Here there are other people. There are a few researchers. You will know them during the master. You know already David Sanchez, who is the director of this master, and there is other important people. For example, we have with us the president of the university, Professor John Macarot, and also the vice president in charge of postgraduate studies, Maurici Mus, and also the Neus Piña is the director of the School for Postgraduate Studies, and also we have with us José María Fuster, who is the president of the Sicomoro Foundation. That is a foundation devoted to the study, to promoting the study of systems in general, in particular complex systems. And this foundation has supported IFISC and the master in several ways. For example, one of you are present, you receive financial support from this foundation. So this is this is just to say you hello, but the important thing is let's start with the presentation of the prize or the recognition for the best teacher of the last year. Okay, sorry. And then the first the president of the university, Professor John Macarot, will tell you some words.
I expected to do that. I didn't know. So, well, good morning to you all. Welcome to those of you who just joined the UIB. So be very, very welcome. I hope your stay here will be a very good one and very productive one in all sorts of ways. And so I'm very aware that you didn't come here to listen to me, so I won't make it long. Just to say that just a few minutes ago, Professor San Miguel and myself were remembering good old times when he taught me. That was back in the last century, 1981, 1982, or something like that. And I can testify to his excellence as a teacher, and it goes without saying, his excellence as a scientist. Well, that has been accredited. And well, just to let you know that IFISC is by and large his making, his idea and his making. So that's it. And I will give the floor now to whoever the director tells me to. So Maxi?
Oh, no, David. So thank you. Thank you. Let me. Oh. Yeah, so it's my pleasure to announce the recipient of this prize. Okay, so on July the 3rd, 2024, the Academic Commission from the Mastery of Physics in Complex Systems decided that Maxi San Miguel should be awarded with the prize with the best teacher based on his merits, okay, which I summarize here. So leadership and collaborations. Okay, so well, for those of you who don't know, though, I think most of you do, So MAXTI was really, let's say, strongly pushed through the creation of this master. Okay, so it was really a person who led this to start this adventure in it was 2012 around, or okay, before that it was of course a lot of work involved. Another merit is the results from the student surveys. Okay, so he always gets very high marks. Okay, which I think the students like his work a lot. So he created, let's say, well, a lot of presentations and materials for teaching. So actually, he was very much involved in the subject computational social science, which is an elective course from the second semester of this master. Well, his commitment is out of question because he has been teaching in this master since the beginning with always a significant amount of credits. And he has also supervised many successful master theses. Okay? So congratulations, Maxi, and the floor is yours.
Hello, yeah. Thank you, Emilio. Thank you, Jaume. Thank you, David, for your words. And thank you also, Maurici, Neus, colleagues and students for being here today. I must say I'm very honored and pleased to receive this teaching award. It makes me happy to have it the last year I will be teaching in this university, and that recognizes what I consider an important part of my professional activity. I want, of course, to thank the committee that decided to give this award to me, especially the director David that created this award, and also to the Sycomoro Foundation and his president for his continued support of the master and sponsoring this award. And I should finally thank all the colleagues that have made this master a success story, including the first director of the master, which was Raúl Toral there, and all the other colleagues, and especially Ingo Fischer, which is not here, but which was the strongest advocate to start this master when there was skepticism about its possible success from other colleagues. Okay, I've been asked to give the opening lecture of these masters, and as such, it is intended mostly to stimulate the engagement of the new students in this field, and that's what I'll try to do. So sorry, colleagues, if what I'm going to say it's too well known for you, but I still hope there will be space for constructive disagreement. So the master is about the physics of complex systems. So two questions at the front are, what are complex systems, and why should I care about them, or what's the use of them? Now, an important person said that complexity is the science of the 21st century. That's Stephen Hawking, which it says it is important, but it gives no information of why it is important or why we should care about that. Now, that's my alternative definition. It is the triumph of emergence over reductionism, which sounds grandiose, but perhaps not too clear. And what I'll try to do in the during these lectures is to try to explain what I mean by that. Okay? Then there is a complex system society, an international society that tries to explain what complex systems are. And they say are systems where the collective behavior of their part entails emergence of properties that can hardly, if not at all, be inferred from properties of the parts. And it gives examples, which include everything it is interesting today. Ecology, human economies, climate, nervous systems, cells and living things, modern energy or telecommunications. So everything that can be of interest today. Now, how do we go to learn about these things? And my approach is, well, let's, to learn about that, let's look at a general phenomena that appears in many different systems and which is a collective phenomena, and then try to extrapolate from them some general ideas. And this collective emergent phenomena is synchronization. Now, what is that? Well, if it works, you will start to see some random white spots that switch on and switch off randomly. Okay, and but after some time, there is a synchronization and there are macroscopic flashes that occupy all the system. Okay, so there is synchronization of these switches that appear randomly, and we go from some type of disordered switching to some ordered collective phenomena. What are these? Those are fireflies, which are a touristic attraction in Malaysia and Thailandia. So complex systems can be good for tourism. And what you see is that they emit light. The other receive them. Those are males. And then there is a feedback, nonlinear effect. They synchronize, and that occupies kilometers of the river. And you can go there and see this. Now, let me give you another example of synchronization. This is what happened in the Millennium Bridge in London when it was opened. The opening day, people were there. They started to step on the bridge, and they synchronized their stepping. There was no general telling them how to step. But then the bridge started to oscillate, and they had to close it. And they had to close it for several years. And this is a social synchronization in the step. Now, let's talk about serious things. Football. What happens in a football stadium? Well, you see La Ola, the wave. This is also a synchronization phenomenon, a social one. Specifically with some delay. Let me give you some more examples of synchronization. For the students, this is different to believe, but in the 70s, the student residents in the universities in the US were separated for male and female. And it was observed, there are several works on that there was a synchronization of the menstruation in the girls in these residents. What happens by the end of a concert? By the end of a concert, people start clapping, but with no one telling them how to do or how to synchronize. By the end, there is a synchronization of this clapping. Again, emerges there an ordered macroscopic type of behavior. More than that, what we have in our heart is 10,000 synchronized cells which act as a pacemaker, and several illnesses are associated with the synchronization or lack of synchronization. Neural synchronization for attention processes in cognitive processes is also that has been studied, and most recently, people even talk about interbrain synchronization, so a collective consciousness, which is something which is being studied today. And then we go to engineering. People have been inspired by this firefly synchronization, and they synchronize a swarm of robots or a group of drones that act synchronized in the field. Okay, now, so this is a very general phenomena, and the question is, how do we study and understand synchronization? If I were a traditional physicist and looking at fireflies, I would ask myself about the wavelength of the light in which they communicate, or what are the mechanism of absorption of photons or whatever. If I were a biologist or more a chemist, I would ask about the sweating substance of the girls that synchronize their menstruation. If I were an engineer, I would look at the materials of the breech. And if I were a psychologist, I would look at what makes me synchronize the clapping or other things like, or the individual attention in a football stadium. Since I am neither of them, what I take is a different global attitude. And the different global idea is which are the general concepts that we are learning and not the specific things of every system. And there are these very specific, these very general ideas. I am not showing you that, but one can reproduce all these phenomena by very simple individual rules. And what I observe is an emergence of collective synchronization. There is no leader, no conductor, no external signal. It is bottom up. What happens is that the local interactions give rise to global behavior, to processes of cooperation and adaptation. And there is this transition from order to chaos that appears when there is a threshold from synchronization. So there are here two very general concepts which, in a way, describe what complex systems are about, which is the idea of emergence on the idea of a threshold. So those are two characteristics of complex phenomena, and I will start looking at the question of emergence. What is emergence? I can offer a definition. Before this definition, this is what you observe in these birds that fly together, and then they create these patterns in space and time that evolve, okay? And they even form the picture of a bird itself. Now, to learn or describe this evolution of these patterns in space and time, it is useless to concentrate in the biology of a single bird or what is the properties of that bird, okay? It is about the interactions. So my definition, well, a definition of emergence is to say that a system has emergent properties when an effective theory of the system at some scale or level of organization is qualitatively different from the lower level theory. And these are the examples of these flocks. Those two are in the skies of Rome, where they appear and evolve in time. And this one is recorded by myself here in Mallorca. Okay? I insist, looking at the individual properties of a flock will tell you nothing about how these patterns evolve and are formed. Now, there are many other examples of emergent phenomena. If you take a tray with some balls, metallic balls or whatever, and you shake them at some frequency, what you will see that appear form is this structure, which is a soliton. This localized structure emerges from the interaction with these balls. Traffic. Traffic is an emergent phenomena from the cars. No one that studies traffic concentrates on how many cars are diesel or what are the properties of this car or what are the mark of this car. It's an emergent phenomenon of the interaction of all the cars. Now, for you, Jose Maria, that we've been discussing that before, from a strictly materialistic point of view, what is the difference between brain and mind or consciousness? I cannot say that mind is just a collection of neurons, even from a, I insist, militant materialistic point of view. It is an emergent phenomena from the interaction of the neurons. And one step beyond, how do we go from the individuals to the society? What society? Social norms, culture, language, institution. Which are all those? Those are emergent phenomena from the interactions of human beings. For those of you that have read this book by Asimov Foundation, it is sometimes said as a precedent of these ideas of emergence. There is this in psychohistory, Sheldon, which was a mathematician, trying to explain history in terms of statistics. Wrong. Emergence is not statistics. It's much more than that. If I'm going back to 1948, there is this paper that I encourage any of you to read, in which he distinguishes 3 types of problems. Simple, solar system. Statistical, ideal gas. And the real problems, organized complexity. So I offer for you now my favorite example of emergence.
Is disorganized. Then comes a perturbation, milk. Every individual starts pushing in one direction. And this is what happens. The pinwheel is an emergent property of the interactions between puppies, whose only rule is to try and keep access to the milk, and therefore to push in a random direction. So it's all about finding the simple rules from which complexity emerges.
Okay. Summarize. Emergent phenomena is a bottom-up phenomena in which order emerges from disorder. The order at larger scales emerges from interactions at small scales, and the individual behavior is not a guide for collective behavior. The slogan of that is attributed to, you know, if you give a lecture like that, you need to quote some of the classics. Aristotle, he said that the whole is more than the sum of its parts, and that's the slogan of complexity. To distinguish between the whole as the sum of its parts and the whole as a single entity emerging from the parts and different from the aggregation of parts. In other words, cutting a horse in two does not result in 2 small horses. Well, this is essentially what I was trying to do in my ideas of reductionism versus emergence. No serious physicist would deny that one of the great successes of physics has been to understand the elementary components of matter, elementary particles, and behind quarks or whatever you want. This has been a great success. I consider myself a serious physicist, and I accept that. But the challenge now is the other way around. Now that we know which are the parts, we should understand how they work together. And this is the idea of emergence. And this is the present challenge. The other challenge is a century old and old-fashioned, in my opinion. Now, these ideas are not that new. I go back to Nobel laureate Phil Anderson, which had this very important paper back in 1972. And I must say that it was a provocative paper addressed the high-energy physics community. Telling them what was fundamental and what was not fundamental. And he says, the reductionist hypothesis does not by any means imply a constructionist one. The ability to reduce everything to simple fundamental laws does not imply the ability to start from those laws and reconstruct the universe. The constructionist hypothesis breaks down when confronted with the 2 difficulties of scale and complexity. The behavior of large and complex aggregates of elementary particles, it turns out, is not to be understood in terms of a single extrapolation of the properties of a few particles. At each level of complexity, entirely new properties appear. If I want to describe a wave in the sea, I should not start by quarks. What he proposes is a hierarchy of science in which the elementary entities of science X obey the laws of science Y. And here you have these examples. But he says, but this hierarchy does not imply that science X is just applied Y. At each stage, going from one to the other, looking at this gap between the disciplines, the interdisciplinary approach, new generalizations and concepts appear. Psychology is not applied biology, biology is not applied chemistry, sociology cannot be reduced to individual psychology. Now, these ideas are associated with what we call the micro-macro connection and emergence. And this is very well explained in this book, which I recommend by everyone. Duncan Batts was, I don't know, he got a PhD in Cornell in mechanics, which we would call here physics, applied mathematics, or whatever. But from there, he went to be full professor of sociology in Columbia University. And from there to Yahoo and Microsoft to get money. But let me read this thing. How do we get from the micro choices of individual in the macro phenomena of the social world? Something like the micro-macro problem comes up in every realm of science, often under the level of emergence, and he refers to Phil Anderson. How is it, for example, that one can lump together a collection of atoms and somehow get a molecule? How is that one can lump together a collection of molecules and somehow get amino acids? How is that one can lump together a collection of amino acids and other chemicals and somehow get a living cell? How is that one can lump together a collection of living cells and somehow get complex organs like the brain? And how is that one can lump together a collection of organs and somehow get a sentient being that wonders about his internal selves? Seen in this light, sociology is merely at the tip of the pyramid of complexity. And each level of this parent, we have essentially the same problem. How do we go from one scale of reality to the next one? And I give here you some examples of this micro-macro connection or complexity. Physics, statistical mechanics, phase transitions, how do we go from atoms and molecules to traps and bubbles? Brain science, how do we go from neurons to perception and cognition? Information communication technologies, how do we go from web page to the World Wide Web? Biology, how do we go from chemicals to life and cells? Semiotic ontologies, how do we go from words to meaning? Social science, how do we go from people to social groups? Business administrations, how do we go from customers to markets? Economics, finance, how do we go from investors to health and crash? Okay, after that, one might try to define what complexity is about. And again, in one of these opening lectures, one should be quote some classics or whatever. It comes from Latin, plexus, which means interwoven or not separable in components. However, it might be more clear, this quote from George West from Santa Fe Institute, complexity is similar to pornography. We don't know how to define pornography, but we recognize it when we see it. Or Kramers, a very famous physicist, that said that in the world of human thought, and in the physical science particularly, the most truthful concepts are those to which it is impossible to attach a well-defined meaning. We have here in the audience Professor Estrada, which has made an effort to try to have a very good definition of what complex systems is about the epistemology. From the abstract of his paper, he defines a complex system as the system where there is a bidirectional non-separability between the identities of the part and the identity of the whole. This is important. Those are things that one has to discuss and reflect. But my point of view is that from a pragmatic point of view, this is not that important. And I challenge any of you to define properly what is physics. And I would certainly contradict that definition. So if we don't have if we don't have a good definition of physics, perhaps it's not time yet to look for a good definition of complex systems. Now, what it is true is that complexity science is not about things, but it is about processes, okay? Being no unique definition of complexity, I put here some of characteristics of this: emergent properties, adaptation, evolution, learning. I've talked about that. Feedback. I've talked about feedback in the fireflies. Now, let me insist now in two other many interesting or important things, which is this idea of multi-level, micro-macro connection, the bridge between the individual and the collective, how to go from organisms to ecosystems, from PC to internet. Going from the individual components up in the scale, we are searching for universality, universal laws that behave global systems. Going down the scale, we go to the organism specificity. And this is normally the collapse of trains between biologists and physicists. The orgasm of a biologist is diversity, specificity. the orgasm of a physicist is universality. So the dialogue will be difficult, and it is difficult. Now, multi-scale, length scale. Here an example. I mean, complexity of the brain. The brain is a prototype of complex system. You have 9 orders of magnitude working together. For those young physicists that at high school were telling you, you have to identify what is the proper length scale of that problem. Well, some problems do not have a fixed length scale or a typical length scale. This is a prototype of one. 9 orders of magnitude working together. Complex systems, such as cities, the human body, or economies, have dynamics on many different scales. The presence of many scales, or even worse, the confluence of scales and lack of a characteristic scale that would allow the breakdown of the problem into sub-problems makes a standard reductionist approach difficult. And this is characterized by self-similarity and mathematical in terms of power loss. The course is on physics of complex systems. So what about physics? If you go to educated people here in campus, or I am afraid even in this audience, and you ask which are the frontier problems of knowledge in physics, you would probably get any of these 2 answers. Subnuclear and small scales, or large scales in the limit of the universe. But those are 2 problems with characteristic length scales, very small or very large. I claim that there are more fundamental and more interesting problems in the problems that do not have a typical length scale. And those are those that exhibit self-similar behavior, scale-free at threshold. And the prototype of that is critical phenomena. In critical phenomena in physics, when there is a transition, you have self-similar behavior. This self-similar behavior is intended to be described here. This is a liquid gas transition, black and white. If you take a part of this thing and you zoom in or you zoom out, what you see is essentially the same, statistically the same. It's invariant under changes of scales. And then this is characterized by the existence of power laws. It is said that a complex system scientist is a hunter of power laws. When you have a power law, that means that you have interaction of many different scales. And this is what happens in critical phenomena, and this is why it is considered the paradigm of complexity. There is a threshold for change of behavior, there is a compromise between order and disorder, there is universal behavior, and there is scale invariance. This was not discovered by physicists, but if we go back to 1896, the Pareto law is, well, it is said that was the first power law that was appeared in the literature about the distribution of wealth. And the distribution of wealth follows a power law. That means that, well, there are people having all types of income. And that to talk, and what happens when you have a power law of that, is that perhaps you can calculate the average, but it is meaningless because the variance diverges, because there are multiple scales. So talking about the mean or the renta per capita or things of that, it is meaningless. Now you have here an artistic view of what self-similarity is about. It is this painting by Salvador Dalí, The Face of War, endless repeating of death and decay. And it is said that this painting was the inspiration for Mandelbrot for his theory of fractals, the omnipresence in nature of self-similarity. You can go to Mercadona and buy one of these things, which shows some self-similar behavior when you zoom or out, or you can go to the Julia sets that appear in fractal theory and see how when you zoom in, you reproduce the same thing and the same thing and the same thing in a self-similar way. Now, so emergence, threshold, multiple length scale. Now, I'm saying that this is about how does the whole work. So the parts are not important, but the interactions are important. How do we describe interactions? The emergent phenomena are conditioned by interactions, and we describe these interactions by networks. Networks is who interacts with whom. Nodes are individual elements, and the links and the interaction between nodes. So a network is the skeleton of a complex system. You have examples of these complex networks, internet, protein interactions. Scientists look at themselves. So who collaborates with whom in writing papers, the mobile phone networks, who is phoning whom. This is Facebook, mobility networks, whatever you want. Now, why these works are called complex networks? Well, because they share two of the characteristics I've told you about of complex systems. The first one is that many of these works are scale-free. This is the network of air transportation in the US. This is the probability distribution that a given airport has K connections. This is the degree distribution. So there are hubs and there are airports with very few connections. The distribution is a power law. There is not the question of what is the average number of connections of an airport in the US is ill-defined. You can calculate that, but it is meaningless. The other property is the small world, which is being halfway between order and disorder. I don't know if you know about this experiment by a psychologist back in 1969 that he asked people in Nebraska to send a letter to someone that they knew with the idea that this was sent until reaching a target person in Boston, okay? And he concluded, well, the experiment, it is like some experiments, they are still continue to be done in psychology and sociology today. It was 300 persons. And they concluded that there were 6 degrees of separation, so that in 6 jumps, you could reach anyone, okay? Now, for those of you in the front row, I don't know, for some of the students, there was something that was called a messenger of Microsoft. That was how to send messages among people, right? Then they redo this experiment, but now with 200 million people and 30,000 million conversations. The answer was the same, mean distance 6.6 links, okay? The small world is this idea that you reach someone in a few steps. How do we model that mathematically? Is these small world networks. You have what we would call a one-dimensional lattice, an ordered network. You delete with probability P some of these links and rewire randomly in the network. If you do that with probability 1, you have a random network. In the middle, you have a small world network, something which is halfway between order and disorder. Okay, so far, complexity, the triumph of emergence over reductionism. And I illustrated that in this way. But let's look. We had cybernetics, we had system science, we had synergetics, we had global systems. Now we have complexity. What's new? Is there anything new in these ideas of looking at the system? Well, what is new is 2 very important things as of today. One is data availability, and second is the direct social relevance of studying these ideas. Let's start with data availability. Well, everyone has heard about the age of big data, the CEO of Google. Every 2 years, we create as much information as we had in the previous years, blah, blah, blah. You go and you have these things of the internet in real time, that in 30 seconds in internet, you are generating close to 700,000 gigabytes of information. This is as we are doing today. And well, you have from all these examples are there. Anyone knows these things. So we have a lot of data. What is the question? Is to extract information from the data and to extract knowledge from the information. I just give you an example of this data because I like it and because it was done here at IFISC, where there is a very large data of geolocalized tweets. And what was done here is to locate people in Mallorca in day 1 and to follow for 1,000 days while they were tweeting to see what is the influence in Mallorca of different places in the world. And this is what you see. First day they are in Mallorca, and this is how they move around in the world. So this is a much more effective way of understanding what is the influence of a given city in the rest of the world than with many blah, 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 right? And you can do that with any city you want. When I was giving lectures on this thing, I was asking our technician, Antonia, to give me the movie for the city I was going to talk. Of course, if you do that in London, the influence is much higher. So again, how do we go from data to information to knowledge? What do we understand when we know everything? We know everything because we have data about everything. And there are very extreme views on that. There is an important or very much quoted paper by Chris Anderson, not the Phil Anderson I mentioned at the beginning, about the end of theory in the data deluge. He says, the new availability of huge amounts of data, along with the statistical tools to crunch these numbers, offers a whole new way of understanding the world. Correlation supersedes causation, and science can advance even without coherent models, unified theories, or really any mechanistic explanation at all. Summary, you are out of business. And many people believe this is the way to go, okay? But I quote Nobel laureate Eugene Wigner, it is nice to know that the computer understands the problem, but I would also like to understand it, okay? Disclaimer, go to this web page and find spurious correlations. Correlations do not imply cause effect. You have here a correlation of more than 99% between US spending on science, space, and technology, and suicide by hanging, strangulation, and suffocation. And you can have all the correlations that you want of this type. One more. According to correlations in medicine, what is the most dangerous thing that you can do in your life is to lie on bed, because with the largest probability, this is where you will die. Okay? So again, what do we understand when we know everything in the middle of this data deluge? The problem is not the capability of data analytics. This is a technical problem, and then it can be solved. It is not only about extracting information, but about extracting knowledge. The challenge is to be able to understand which are the mechanisms which are behind the data that we have to understand this data. And understanding is to know why. And to know why means to understand which are the mechanisms that allow to establish cause-effect relations. And this goes beyond inference from statistical correlations. Understanding means modeling to understand data. And this goes beyond modeling to reproduce data. And this means to understand the underlying mechanisms beyond describing which are the patterns of behavior. So from an old-fashioned physicist point of view, what model means? Model is a word that has very different meanings in very different communities. For me, and for many physicists, the idea of a model is that I have some data that I want to understand. And then I construct some theory, some mechanism, some model, and there is feedback between these two things until this theory or mechanism explains or understands this data. And then I might have some parameters which are input data. A different way is I have data that I want to reproduce. I do some inference and I have a model. This is what is called a model. This is very sophisticated and useful parameter fitting or data fitting. And this is very important to do prediction in short time. But it is, for me, not much in understanding. Then my claim is that there is a clash of titans. Inductivism, data-driven, big data, inference, deductivism, Karl Popper, model-driven. And complexity science might be the discipline in which both of these approaches merge as one. This is about data. Second is complexity science. What for? Well, there is always this debate about curiosity-driven science and applied science, which I think is not a proper debate, but it is there. So to start with something, I will quote one of the most famous physicists, Richard Feynman, said, physics is like sex. It's like sex. Sure, it may have some consequence, but that's not why we do it. Well, that's most of science. It is curiosity-driven, but then there are consequences about that. Let me start about, well, what for complexity science, because it's fundamental and frontier of knowledge science that we need to do. This was recognized 3 years ago by the Nobel Prize that was given for groundbreaking contributions to our understanding of complex physical systems. It was a shared prize between Giorgio Parisi for the discovery of the interplays of order and fluctuation in physical system atomics and planetary scales, and for Manabe and Hasselmann for the physical models of Earth climate. Many people did not understand this as a joint Nobel Prize. They thought there were two separate things, one on climate and one on things that no one cares and no one understands, or what is this about, okay? Now, let me try to explain why this is a joint prize on complex systems. First thing, climate change. What is climate? Climate is an emergent phenomena in the complex systems Earth. And it's a prototype example of examples with interaction at many different scales, from local variables to ocean-atmosphere coupling to planet-level correlations. So it's a proper complex systems. Prediction. Let me quote this sentence by Giorgio Parisi. In the study of complex systems, the word prediction has a weaker but more general sense, so that the target field of physics is much broader and physics constructions, concepts, models, tools have much more applications. The idea is predicting one more number in a universal constant. This is very important in prediction in all traditional physics, but this is not the target of what we are doing now. And I don't know how many of you are aware that when you listen to the weather prediction in the TV, this is just done by the average of many different models. So it's based on realization of different models. These models is what Parisi called replicas in his study of disordered systems. And of course, interdisciplinarity. I mean, both of these type of things are, in particular, Parisi has been working in physics, but also mathematics, biology, flux, neuroscience, and machine learning. Now, social relevance. Well, complexity concepts, in my understanding, are needed in daily life arguments, because it allows to destroy counterintuitive results or goes against common wisdom. And I put you here an example of what was considered a first sentence of emergence in social science. This is Thomas Schelling received the Nobel Prize in Economics back in 1978. He has a beautiful book on micromotives and macro behavior, micro-macro connection. And he states, warn against jumping to conclusion about individual intentions from observations of aggregates, or jumping to conclusions about the behavior of aggregates from what one knows or can guess about individual intentions. I mean, it is not as simple as you listen in the news. This has happened because of that. Well, let's see. Okay? Emergence is a complicated thing. Many of you, at least the oldest, will know who is this lady, the strongest advocate of economical liberalism in the UK, and had this famous sentence: there is no such a thing as society. There are individual men and women. So in my understanding, no idea about what emergent phenomena is about. There is this other famous guy. Society is not made about human beings, but constructed in terms of their communications. In my opinion, he had a better theory, but no political statement. Applications did not work. So As I said, there are many meaningless concepts: the average income per capita, the average number of friends in an online social network, because those are power laws. And complexity science is relevant to try to educate policymakers. It should help policymakers to break free from their propensity for linear thinking, proportionality thinking, and promote greater sophistication in their perception of cause-effect relations. There is this famous paradox in which there are two roads that are collapsed by traffic. And the first politician arrives and says, well, the result is to construct another road here. Wrong. It creates more problems in traffic. So one has to be a little bit more sophisticated. In summary, in my understanding, complexity science or looking at complex systems is a new way of thinking that could transform society, and this is the social relevant, by transforming the way of thinking. And this should entitle a new education system. A new education system, this is a teaching award, in which students of all ages learn the new way to learn about reality. And it is learning across disciplines, not learning in ghettos, and learning from that. Now, this is my view of new fields outside traditional physics, where there is the frontiers of knowledge, the frontiers of research coming from complex systems with some social relevance. Socio-technical systems. This is about interactions of human and technology, interactions around information, communication, technology, and social behavior. Fake news, whatever you want, all this type of interaction, how do we? And then robot-human interaction and collective robot behavior. This is a frontier of knowledge that could be addressed. Complexity engineering is not only about learning about complex systems, but about designing complex systems for specific tasks. Control, for instance, systems for non-conventional computing. This is something which is also done here at IFISC, defining hardware to new ways of computing. Global change and system errors, coupling of natural phenomena and human activities. Neuroscience, models of brain functional networks. How we understand perception, cognition, attention, emotion. How from there we learn something about diseases. Health science. Well, a few years ago we had these pandemics, and we learned that to understand pandemics, it was not only about biology, but it was also about human mobility and social interactions. Now, there are many interacting factors for personalized medicine. So the analysis of data is something that is important here, and big data analysis of clinical records. Now, these are new fields outside traditional physics, and this is a Master of Physics of Complex Systems. Most of the students here have a physics background, and I am telling them that this is the future outside traditional physics. I started saying that the lecture was to motivate the master students, so let me finish with a quote from Duncan Batts-Glynn explaining why there is a brilliant future for them. Physicists, it turns out, are almost perfectly suited to inviting other people's disciplines, being not only extremely clever, but also generally much less fussy than most about the problems they choose to study. Physicists tend to see themselves as the lords of the academic jungle, lovely regarding their own methods as above the ken of anybody else, and jealously guarding their own terrain. But their alter egos are closer to scavengers, happy to borrow ideas and techniques from anywhere if they seem like they might be useful, and delighted to stomp all over someone else's problem. As irritating as this attitude can be to everybody else, and I can tell you that it is irritating, and they let you know that they are irritated, the arrival of the physicist into a previously non-physics area of research often presages a period of great discovery and excitement. Mathematicians do the same thing occasionally, but no one descends with such fury and in so great a number as a pack of hungry physicists adrenalized by the scent of a new problem. Thank you.
Thank you, Maxi, for this inspiring lecture, as always. And there is time for 1, 2 questions if someone you want to ask something. And well, we will have 1 year to ask questions. and if not, then let's let the president of Sycomoro Foundation to present to Maxine, if you want to say something, but also.
Gracias. Gracias, José. Gracias, José María. Muchas gracias. Gracias.
So that's the nearly the end of this activity. Now the most important is there is coffee and cookies there. And the second most important, remember that at 11 we have a class in the Alcover building. It's just in that direction. So thank you everybody, and thank you Maxi, and enjoy the coffee now.
¿Han sido 45 minutos? ¿Cómo? Digo, 45.
Sí, muy bien, muy bien.
Bueno, te he provocado un poco, ¿no?